Every star you have ever seen is in the middle of its life. You have never seen a star being born. You have never seen one die. Both processes happen on timescales so far beyond a human lifetime that from where we stand, the sky looks frozen. It is not. Stars are born, burn for millions or billions of years, and then end. How they end depends entirely on how big they were. This is the full story. Birth to death, all of it. This is Beyond the Cosmos. We go deep on space science one question at a time. Subscribe so you do not miss what comes next. Stars are made from gas and dust. Most of that gas is hydrogen, the simplest and most abundant element in the universe. It has been drifting through the galaxy since the Big Bang. Vast clouds of it, cold and dark, exist between the stars. They are called molecular clouds, and they can stretch for hundreds of light years. For most of their existence, these clouds just float, but occasionally something disturbs them. A shock wave from a nearby supernova, a collision with another cloud, a density fluctuation in the galaxy's spiral arms. Whatever the trigger, one region of the cloud becomes slightly denser than the rest. Gravity does the rest. The denser region pulls in more material. The more material it pulls in, the stronger its gravity becomes. The process accelerates. The cloud begins to collapse inward, slowly at first, then faster. As it contracts, it heats up. A rotating disk of gas and dust forms around the collapsing core. Smaller clumps in the disk may eventually become planets. At the center, a protostar is forming. It is not a star yet. It is hot and bright, but not yet hot enough to sustain nuclear fusion. It is still growing, still pulling in material from the disk around it. This phase can last hundreds of thousands of years. The moment a star is born has a precise definition. It is the moment nuclear fusion begins in the core. When the protostar has accumulated enough mass, a small amount of mass is converted directly into energy. That energy pushes outward against the inward pull of gravity. The collapse stops. A balance is reached. The star settles. This balance between the outward pressure of fusion energy and the inward force of gravity is what defines a main sequence star. It is the state the Sun is in right now. It is the state most stars spend the vast majority of their lives in. How long a star stays on the main sequence and what happens when it leaves depends almost entirely on one thing: its mass. Not all stars are alike. The smallest stars, called red dwarfs, have masses as low as about 8% of the Sun. They burn so slowly and so dimly that they can sustain fusion for trillions of years. The universe is not old enough for a single red dwarf to have died of natural causes. They are the most common type of star in the galaxy, making up roughly 70% of all stars, and almost none of them are visible to the naked eye. Stars like our Sun are mid-sized. They burn for around 10 billion years. The Sun is currently about 4.6 billion years old, roughly halfway through its life. At the upper end, massive stars, those with 10 or more times the mass of the Sun, burn so hot and so bright that they exhaust their fuel in just a few million years. Some of the most luminous stars known are hundreds of thousands of times brighter than the Sun and will live for only a few million years before they die violently. Mass is the single most important variable in a star's life. More mass means more gravity, more pressure, higher temperatures, faster fusion, shorter life, and a more dramatic death. A small star lives quietly for an almost incomprehensible length of time and fades gently. A massive star blazes through its fuel and ends in an explosion that briefly outshines entire galaxies. Calm and slow, the most unhurried section. This is the long, stable middle. For most of its life, a star does not do anything dramatic. It burns hydrogen in its core. It holds itself in equilibrium. It warms the space around it. If it has planets, they orbit. Time passes. Billions of years of it. The Sun has been doing this for 4.6 billion years. It will do it for roughly 5 billion more. From the outside, nothing appears to change. But inside, the supply of hydrogen in the core is slowly being converted to helium. For a star like the Sun, or anything smaller down to about half a solar mass, the end is slow and relatively quiet. When hydrogen in the core runs out, fusion moves outward into a shell around the core. The core, no longer generating energy, begins to contract under its own gravity and heat up. The outer layers of the star respond by expanding outward, pushed by the increased energy from the shell. The star becomes a red giant. It swells to many times its original size. When our Sun reaches this stage in about 5 billion years, it will expand far enough to engulf Mercury and Venus. Earth's fate is uncertain, but its surface will be scorched beyond any possibility of survival long before the expansion reaches its maximum. The red giant phase is not stable. Over time, the outer layers of the star are shed into space in expanding shells of gas, lit up by the radiation from the hot core within. This is called a planetary nebula, a name that has nothing to do with planets. It is simply what early astronomers thought these glowing shells resembled through early telescopes. What remains at the center after the outer layers are gone is the core itself, a white dwarf. Roughly the size of Earth, containing most of the original star's mass, no longer fusing anything. Just a dense, hot, slowly cooling remnant that will shine faintly for billions, possibly trillions of years, before going dark entirely. No explosion, no violence. The small star ends by letting go, layer by layer, until only the core remains. Massive stars die differently, completely differently. A star with more than about 8 times the mass of the Sun burns through hydrogen quickly, then moves on to fusing heavier elements. Helium fuses into carbon. Carbon fuses into neon, then oxygen, then silicon. Each stage produces less energy and burns faster. The star is racing through fuel it cannot replace. At the end of this chain, silicon fuses into iron, and iron is the end of the line. Iron cannot release energy through fusion. Fusing iron requires energy rather than producing it. When an iron core builds up at the center of a massive star, the energy source that kept the star inflated against gravity simply stops. The core collapses. In less than a second, a core the size of Earth compresses to roughly 20 kilometers across. The outer layers of the star, which were falling inward, hit the collapsed core and rebound outward in a catastrophic shockwave. The star explodes. This is a core collapse supernova. It releases more energy in seconds than the Sun will produce in its entire lifetime. The explosion scatters the star's outer layers across space at thousands of kilometers per second, seeding the surrounding gas with carbon, oxygen, silicon, and every element heavier than hydrogen and helium that the star spent millions of years producing. The elements in your body, the carbon, the iron in your blood, the calcium in your bones, were forged inside stars that exploded before the Sun was born. You are, in the most literal chemical sense, made of dead stars. What the supernova leaves behind depends on how much mass the core had. If the remnant core left behind by a supernova has a mass between roughly 1.4 and 3 solar masses, it becomes a neutron star. An object the size of a city, denser than anything except a black hole, spinning rapidly and emitting beams of radiation that sweep across space like a lighthouse. If the remnant core is more massive than that, there is no force in nature that can stop the collapse. Gravity wins completely. It becomes a black hole, a region of space where the gravitational pull is so intense that nothing, not matter, not light, not any signal of any kind, can escape from inside the boundary called the event horizon. Stellar black holes formed this way typically have masses between about 5 and 100 times that of the Sun. They are not rare. The Milky Way is estimated to contain somewhere between 10 million and 1 billion stellar black holes, most of them invisible and silent in the dark between stars. If you made it to the end, you now know more about stars than most people ever will. Subscribe if you are not already here. Like the video if the stellar life cycle surprised you. And drop a comment telling me which stage of a star's life you find most fascinating. Next time, we keep going deeper.